Last time we saw a bunch of different smart contracts in Bitcoin. Basically, we saw how we can write, how we can combine many different scripts to get things that kind of mimic real-world financial contracts. So, for example, we were doing an escrow, and of course, an escrow in the real world is just a financial contract. So we were doing something more than just transferring money. We were actually programming with money, and we were saying that you can get this money under certain circumstances, right? So that's what we call a smart contract, at least in Bitcoin. Today, we're going to see a more general definition of smart contract, which is like the Ethereum-like smart contracts. But before that, I'm going to just show you one last Bitcoin smart contract. And this is what we use for micropayments. So as usual, imagine that we have two people. We have Alice and Bob. And in this scenario, Alice wants to pay Bob for some sort of on-demand service. So imagine that Bob is, for example, a mobile service operator. So Alice wants to make a phone call. She has to pay for every minute of the phone call. Okay. So Alice wants to pay Bob. Let's simplify it and say $1 Hong Kong per minute for some sort of phone service. Okay. Now, well, what's the issue? She can, of course, pay using Bitcoin. The issue is that, again, none of the two parties trust the other party. Okay. So Alice is not willing to pay first, because if she pays first, maybe Bob doesn't provide the service. And Bob is not willing to provide the service first and let Alice make her phone call, because maybe when her phone call is finished, Alice doesn't pay. Okay. So this is a very common thing in this course. No one trusts anyone else. Okay. So that's our first problem. But the second problem is that the payment here is really small. Right. So Alice, if she makes, let's say, a 5-minute phone call, she's going to pay only $5 Hong Kong. And imagine doing that on the Bitcoin blockchain. You have to create a transaction. That transaction has to be picked up by the miners and added to a block. But we saw that in order to incentivize the miners to include your transaction, you have to pay a transaction fee. Now, the transaction fee itself is something like 400 Hong Kong dollars. Right? So if you want to pay only 5 HKD, you don't want to pay 400 HKD in fees. So that's our second problem. So no one trusts anyone. That's our first issue. And the second issue is that we want to avoid transaction fees. Okay. Now, we're not going to be able to completely avoid transaction fees, because, I mean, at the end of the day, there should be a transaction, and that transaction should have a fee. Otherwise, I'm not even using the blockchain. But at least I want to minimize them. Maybe, let's say, I want to make one transaction today, and then I want to avoid doing any other transactions until next month. And I want to be able to pay for all of my phone calls between these two transactions. Okay. Now, here's the really clever idea. Alice is going to create a transaction. That's my thing. Oh. Okay. So this is the transaction that Alice is going to create. And she's going to basically put a deposit. So let's call this transaction 1. It has some input. Let's say maybe a huge amount, 5,000 Hong Kong dollars. And this is coming from Alice. Now, the output is just like the case of the deposit. So I say that you can use this only if both sides agree. So, of course, I have this output and then I have another output. I have this output and then it's less than 5,000 because it has to pay some transaction fee as well. But whatever, in this output, I'm going to say you can spend it if you have a signature from both Alice and Bob. Okay. But remember, we said that there are two types of signature requirements. I can require the signature to be on the entirety of the next transaction or only on part of it. And I'm going to say I require the signature to be on the entire transaction. So signature on the whole transaction. So, and by this, I mean the transaction that is spending this coin. And I need signatures by both Alice and Bob. Okay, so if both of them agree, this money can be sent. And let's say that this money is 4,500 HKT. Okay. Of course, these will be denominated in Bitcoin, but I'm just using HKT here. Now, the idea is that Alice has to pay Bob for every minute. So at first, Alice pays Bob for the first minute of the call, and then Bob allows Alice to make 1 minute of a phone call. And then at the end of the first minute, she has to pay for the second minute and so on. So Alice is going to create a series of transactions here. This is the first transaction she's making. Actually, I just realized it's better if I call this one transaction 0. So let's call this one transaction 0. Alice creates a transaction 1, which uses this output as the input, and then pays 1 HKD to Bob and the rest to Alice. Of course, it also pays some transaction. Okay. Now, we've talked about this before. Bob is not sure that he would be paid at this point because this transaction is not on the blockchain and it doesn't have confirmations and all of those things. But Alice just creates this transaction, signs it, and sends it to Bob. So now what does Bob know? Bob knows that this transaction 1 is signed by Alice. So if Bob wants to, he can sign this transaction at any time and it would become a valid transaction and Bob can publish it. Okay. At the same time, this money is stuck here. So Bob is sure that Alice cannot spend this money without his consent. So at this point, even though this transaction is not published on the blockchain, Bob is sure that he's getting his 1 Hong Kong dollar. Okay. But Bob is not going to publish this transaction. Bob is going to wait. So Alice sends this transaction to Bob. Bob verifies it, allows Alice to make 1 minute of a phone call. And then at the beginning of the second minute, Alice is going to send another transaction to Bob. This is now my transaction 2. And this transaction is again going to do double spending, basically. It's going to use the same input, but now it's giving 2 HKD to Bob and the rest to Alice. And so on. At the beginning of every minute, so at the beginning of the ICE minute, Alice is going to send the ICE transaction to Bob. This is transaction I. And all of these transactions are going to use the same input. The same input comes here. And then IHKD is paid to Bob. The rest is paid to Alice. Okay. Now, why does this work? So suppose that Alice hangs up after I minutes So she has made a phone call for I minutes. We want to make sure that Bob receives exactly IHT. Right? So Bob has received all of these transactions from Alice, and all of them were signed by Alice. Bob verified that they were signed before he allowed the conversation to go on. Okay. Now, so Bob can sign any of these transactions and can publish this transaction on the blockchain. And it will eventually give this money to Bob, right? But Bob cannot publish more than one of these transactions because they're all double spending the same coin. They're all using this coin here. So if Bob tries to do something dishonest, if Bob tries to publish more than one of these transactions, at most one of them will end up on the blockchain. And of course, from Bob's point of view, it's better if this last one ends up on the blockchain because in this case, he gets paid the most. So if Bob is rational, if Bob wants to just maximize his own payoff, he will only sign the last one and publish the last one on the blockchain. Okay. So in this case, Alice is sure that she's paying exactly the right amount for her phone call. And Bob is also sure that he's getting paid. There is, a small risk. Maybe there's a risk of 1 minute. Maybe Alice pays for the ice minute and Bob doesn't provide that last minute, but that's not a big risk. We don't care about that. But just like all the protocols before this, we have to always think of all the possible attacks on our protocol. Now, how can one of the parties do an attack? Well, we can have extortion again, and we can have extortion by Bob. So imagine that Alice has made a phone call for only 10 minutes. And so this I is 10. She has given all of these transactions to Bob. But Bob just says, your money is locked here. I'm not going to publish any of these transactions. So I'm going to take your money hostage. And either you give me another transaction that pays me more of the money, or I'm just going to let it stay there. Right? So we want to avoid this kind of situation as well. And to avoid this, we can just change this condition that we had on our coin. Instead of saying that you can use this coin if you have a signature by both Alice and Bob, we can also put a time lock on it. We can say that if some particular time has passed, then Alice can just get her money back. So I'll change this script to say you can spend this money if you have signatures on the entire transaction by both Alice and Bob, or if the time is after some predetermined time, so the block number is more than some constant that we're going to choose, and you have a signature by Alice. Okay, so this makes sure that Bob cannot extort Alice. So Bob can publish at most one of these transactions, but now he also has a deadline to publish them. He has to publish them before block C, because as soon as block C passes, Alice can just spend this money on her own. Okay, so this ensures that Bob publishes exactly one of them and everyone is happy. Now, imagine if Alice wanted to make many phone calls, she could just use 2 transactions. The important point here is how much are we paying in transaction fees, or to be more specific, how many transactions end up on the blockchain? How many times do we have to actually pay for transaction fees? And the answer is 2. Because even though we're creating all of these extra transactions, only the last one is going to end up on the blockchain. So I'm paying transaction fees for transaction 0 and transaction 1. Right? So you can imagine that, I don't know, Alice can put this deposit at the beginning of the month and then use it to make all of her phone calls during the whole month. Okay, so this kind of thing is actually called the channel. This is called the channel between Alice and Bob. Now, basically, the really interesting point here is that we can effectively transfer money from Alice to Bob without actually putting a transaction on the blockchain, right? So if Alice wants to just pay one more HKD to Bob, she just signs another transaction here and sends that to Bob. We don't need that transaction to be on the blockchain before we can be sure that the transaction is done. So this actually allows us to have instant payments, because the whole problem with the blockchain was that I had to wait for confirmations. I had to do all of those things. I had to wait for my transaction to get into the blockchain, and then 6 blocks come after it. And that took a whole hour. But here, when Alice wants to pay a little bit more to Bob, she just signs a new transaction, sends it to Bob. And Bob is sure that he will receive his money, right? So as long as we create this deposit transaction first and put it on the blockchain, then afterwards we can have instant transactions between Alice and Bob. And then you can imagine that we can have many different people who have channels between themselves, right? So imagine that I have a bunch of different people. So let's say I have another network. This is not the blockchain network. It's just some other network. And people in this network have created channels between each other, which means that basically they have put transactions like this on the blockchain. They have made some deposits. So for example, maybe this is Alice and this is Bob, and they have a channel with some capacity, and the capacity is like the amount of money that can be transferred in that channel. So in this case, 4,500. And then maybe Bob has a channel to someone else. They might have channels, and so on. So let's say this is Carol. Let's say this channel is 2,000. Now, suppose that you want to pay some money to Carol, right? Suppose that you want to pay 10 Hong Kong dollars to Carol. You can, of course, make a Bitcoin transaction and put the transaction on the blockchain and all of those things, but then you will have to pay a ton of money in transaction fees. Or you can just go to Bob and say, hey, Bob, you have a channel to Carol, so you can make an instant transaction with Carol. So I'm going to just pay you 10 Hong Kong dollars plus some much smaller fee, and then you make the instant transaction to Carol, right? And of course, we can also chain these transactions. So if I don't know Bob, but I know Alice, I can pay 10 Hong Kong dollars to Alice, like let's say by bank transfer, and then Alice pays Bob and Bob pays Carol, right? And all of these transactions are, again, instant transactions, because it's just using these kinds of things. Now, again, of course, creating the channel takes some money because they have to pay transaction fees. So in order to use other people's channels, you have to probably pay them some small transaction fee as well. But that transaction fee is much smaller than the transaction fee on the Bitcoin blockchain itself. Okay. And also your transactions are now instant, which is much better than Bitcoin. This kind of thing is actually called the Lightning Network. It's basically a network built on top of Bitcoin that allows you to do these kinds of transactions. Technically, they don't use exactly the kind of channel that I showed you here. They have a different type of channel. It's a two-sided channel where both sides can pay each other. I'm going to put a YouTube video on Canvas for you to watch if you want to. But the main idea is this. The main idea is that as soon as you can have instant transactions, you can pay other people to do the transactions on your behalf. And then you can create a network of all these people who have channels with each other. And in total, the transaction fee that you pay on the Bitcoin blockchain is actually very small, because you pay one transaction fee when you open the channel, when you send this transaction, and then you pay one more transaction fee when you close the channel, when you send the last transaction. So it's 2 transaction fees per channel, but in each channel, you can do a lot of transactions. Okay. So that's all we wanted to cover in this course about Bitcoin. We are now going to look at a more complicated and more advanced blockchain. So we're starting a new module. This is Ethereum. Now, the idea here is that we want to have more expressive smart contracts. So I told you that Bitcoin has a scripting language, and you can write conditions for how to spend money there, and we use them to write some financial contracts, of course. But these scripts are very limited, right? So Bitcoin scripts, they can do some basic operations, they can compute hashes, they can verify signatures and so on, but they cannot do everything. For example, they have no loops, or there is no functions and recursion in there. So the programming language is really limited. Now, why is that? Why is the programming language limited in the first place? The reason is to basically avoid denial of service attacks. So imagine if I could have a loop in my Bitcoin script, then I could potentially write a loop that never terminates, right? So imagine if I had, for example, this transaction, and there was a script attached to this coin, and then the script of this coin said that while 1 is greater than 0, just compute some hash. Okay. So this is a script that never terminates. I cannot allow this, because if I allow this kind of thing, when someone wants to spend this coin, everyone on the network has to run this script. So every node on my network gets stuck, right? So Bitcoin just said, we're not going to have loops. We're not going to have functions, because if you have functions, you can have recursion, and then you can basically create a loop. And we're also not going to have all sorts of operations. We're going to have a very limited number of operations. And actually, as time is passing, they're canceling and disabling more and more operations in the Bitcoin programming language, because they're finding new attacks and they want to avoid the attacks. So the miners on Bitcoin actually have a whitelist of scripts right now. So if you write any new script, the miners would just not allow it, because they think it's probably an attack. So all of these problems led to other more advanced cryptocurrencies that actually support more expressive smart contracts, and Ethereum is one of them. Now, the idea here is to go back and look at the blockchain protocol at a very fundamental level. So the blockchain protocol was about reaching consensus, right? Remember, we had this idea that we have a chain of blocks. So we have B0, B1, B2, and so on. And then every block basically contained a bunch of transactions, right? So in B0, I had a bunch of transactions, maybe transaction 1, transaction 2, so on. In B1, I also had transactions. So at the end of the day, this was giving me a consensus on transactions, okay? The point of blockchain, the point of the blockchain protocol is to reach consensus on transactions. Now, consensus on the list of transactions, of course, and also in their order. So on the history of transactions. So I need to know what transactions have happened in the past and in which order. And that's what the blockchain protocol gave me, right? Now, here's the idea in Ethereum. You say there is nothing special about transactions. So if you look at transactions in Bitcoin, they're basically just transferring money, right? They're sending money from Alice to Bob. Sometimes they have some more complicated scripts, but that's basically what they do. But if you look at the blockchain protocol is giving us a consensus on the history, and it doesn't really care if that history is a history of transactions, right? I have proof of work, And proof of work is giving me the consensus anyway. So instead of having consensus on transactions, I can maybe not have a monetary system at all. Maybe I have just a bunch of messages between people. Imagine that this is a messaging service now, and I just want to reach a consensus about the messages that everyone has sent. Right? That would also work. So instead of transactions, I can just put messages. Generally speaking, I can change the definition of transactions, and I can have whatever I want instead of transactions, and I can reach a consensus on the history of those things that I want. So I can extend the idea of what a transaction can do. Now, Ethereum really does the maximum possible extension here and says that a transaction can do many new things. So in Ethereum and also in other programmable blockchains, a transaction can do these things. So generally, let's say that transactions are one of three types now. So it can, of course, transfer money. That's what it did in Bitcoin. Okay. Transfer money. This is simple. This is all we've had in this course until now. But it can also deploy some code on the blockchain. And this is new. So the second thing it can do is that it can contain some piece of code, okay? And it can deploy some code, let's call it C, on the blockchain. Now, what does this mean? It just means that my transaction, instead of having the normal metadata that these are the inputs, these are the outputs, like this is who I'm paying and so on, it's just going to say, I carry a bunch of code and here is the code. And that code is part of the transaction. So when I put this kind of transaction in, everyone on the network is going to see the code. When the transaction is taken by some miner and added to the blockchain, the whole code will be part of the consensus. So everyone on the network agrees about what the code C is supposed to be, right? Again, the whole point here is consensus, agreement. We want to make sure that everyone has the same code. Now, the third thing that a transaction can do, which is very interesting, is that it can call functions of the codes that were deployed in previous transactions. Okay. Functions of deployed codes. Okay. Now, this might not make sense to you yet, but it will very soon. First of all, we're going to call these codes smart contracts. And there is nothing smart about them. It's just a marketing trick. So someone called it smart contract. Everyone is calling it smart contract. In this course, actually, we usually just say contracts. Now, what's interesting about this? The interesting point is that when you put a piece of code on the blockchain, everyone reaches consensus, so everyone knows what this piece of code is. And then when you later on call a function, and of course, when you call a function, you can also give the parameters that you want to pass to that function. Again, everyone on the network can execute this function call, and they can see what the result was. So for example, maybe your code has a variable x, you have a function, you call that function, and it sets the value of x to 10, let's say. Then everyone on the network would agree that the value of x is 10. So I can do something like this. I'm writing pseudocode in this session, but from next session, we will actually write code. So let's say I have this C here, which is my code, and it just has a global variable x, okay? And let's say it also has a function called set, which takes some value y, and it just sets X to be equal to Y. Okay, this is my code. Now, I'm going to first create a transaction that contains this code. And that's the deployment transaction. Okay, so step one is create a transaction containing C. Now, of course, I have to sign it. I have to do all the normal things. Every transaction has to have some originator, someone who's created this transaction, and it should be signed by the person who created this transaction. Okay? So I create a transaction containing C, and I just use the gossip protocol to announce this transaction to everyone else. Now, just like Bitcoin transactions, you can imagine that this transaction also has a transaction fee. So the miner will take this transaction and at some point add it to the blockchain. Okay. Now, to think of this transaction at this point, we're going to really simplify stuff, as I normally do in this course. Later on, I will give you much more details. But for now, just imagine that this is a transaction like a Bitcoin transaction. So it has a bunch of inputs. Let's say it doesn't have any output. So all of the inputs are paid as transaction fees to the miner. Okay. But additionally, this transaction is going to contain a field, let's say called code. And in that field, it's going to include the code of this program C. Okay. So it's just some metadata that I'm adding to my transaction. Now, when this transaction gets added to the blockchain, remember, everyone is reaching consensus about the transaction, so everyone knows what this code C is supposed to be. So at this point, every node on the network agrees on C. Now, in the next step, in step 2, I can create another transaction which calls the function set. And let's say it gives the value of 10 for Y. Okay. So I create another transaction. And all it does is, again, just like before, I have my transaction. I have some input. I don't have any outputs. The only reason I have the input is to pay some transaction fee, let's say. And then here, I'm going to say I want to call a function. And the function I want to call is going to be the function set in C. Now, how do I point to C? Well, I can use a hash pointer, right? If C is already in this transaction, and this transaction is already on the blockchain, I can have a hash pointer to this transaction. So I can point to this transaction. I can say there is a code C in this transaction, and that code has a function called set. And that's the function that I want to call. Okay. So I say that the function is this, and then of course I have to give the parameters that I want. And in this case, I just have Y. So I say I want to call it with Y equal to 10. Okay. Again, this is just like a Bitcoin transaction, except that it has some extra metadata. It has the function and the parameters. Now, I publish this on the blockchain. Just like before, when a miner adds it to the blockchain, everyone reaches consensus about the order of the transactions. But now, additionally, every node, whenever they see a function call, they're going to also execute it. Okay? So every node is going to execute this function set, and every node is going to see that the value of X now changes to 10. Right? Now, this is interesting because everyone can reach consensus not only about the codes, but about the current state of every contract, which means every variable in every contract is subject to consensus. Everyone on the network has the same view of all of them. Okay? Now, why would I care about this? Like, how does this help me with money? How does this help me with writing financial contracts? This is the last piece of the puzzle, which makes things really interesting. And it's that these pieces of code, these contracts, they can actually own money. Okay. So you can send money to a contract. So let's say C. And then the contract owns that money, which means that you can get the money back only if the contract allows you. So in our contract programming language, we're going to have a special operation that is used for transferring money. And whenever you give money to a contract, you can get it back only if the contract decides that you can get it back, only if there is a sequence of function calls in which the contract finally says, I want to transfer this money. Okay, so you can send money to C, and the money is under C's control. Okay, let me give you an example. Suppose that I want to create a puzzle contract. So let's say I have some particular value in mind, and I want to say, if you can invert a hash function, I'm going to give you a reward. Okay, very similar to proof of work. So let's say I have some value, I don't know, 1, 2, 3, 4, and I want to give a reward. I want to give, let's say, 10 Ether, and by the way, that's the unit of currency on Ethereum, to anyone who finds some value X such that the hash of X is some particular value that I like. Okay, so I don't know. It's something like this. Okay. Now, how can I do something like this? Well, I first have to write my contract. So step 1 is to write a contract. Okay. Now, here's my contract, and it's actually pretty easy. I'm going to call it C puzzle. It's going to just have one function. And that function, I'm going to call it claim. And it's going to take some integer X. And all this function does is that it computes the hash of X. And it says if the hash of X is equal to this value that I liked, then pay all the money in this contract to the person who made this function call. Now, how am I going to write that? Well, let's say I write it like this, pay. Now, how much do I want to pay? I want to pay all the money that this contract has. So cpuzzle.balance. Now, who do I want to pay it to? I want to pay it to the caller of the current function. Okay, so I just say function caller. So whoever provided this X. This is my smart contract. Again, this is in pseudocode. We will soon see how to write it in the actual language that is used for contracts usually, which is Solidity. But this is the contract that I'm going to write. And now I'm going to deploy this contract on the blockchain. So my second step is basically publish a transaction that contains this code. Okay, and then of course I have to wait for that transaction to get added to the blockchain. But as soon as this transaction gets added to the blockchain, I can now point to my code. I can now have a pointer to my code. Because this code is in some block, right? The transaction is in some block. I can use the hash of the transaction as a pointer to that transaction. And then I can use the name of my contract. So if I want to point to this particular function claim, I would say, go to a transaction with this hash, look at the contract with this name, cpuzzle, and look at the function with this name, claim. So I would just write hash.cpuzzle.claim. Okay. But here's the thing. At this point, this code is deployed on the blockchain. Everyone knows about it. But unfortunately, it doesn't have any money, right? So my contract is just a piece of code. I have to actually give it some money. So this is my third step. I say transfer, let's call it 10 Ether to this cpuzzle. Okay. Now, if I go back here, I said that a transaction can either deploy some code, which is something that we have already used, or it can transfer money, which is what we had in Bitcoin already. The difference is that in Bitcoin, when you wanted to transfer money, you had to always say, what is the public key of the recipient? But now you can transfer money not only to external recipients, but also to contracts. Again, how do you point to a contract? You can use a hash pointer, right? So I can transfer money to a contract, to a smart contract. Okay. So here I'm going to transfer some money. So now my contract owns 10 Ether. It's the contract's money. No one can take it away from the contract unless the contract itself gives it out. But this contract would give out the money only if someone can call the function claim and give the right value of X. So now everyone on the blockchain can see this contract. They can try to solve it if they want to. If they find the value of X, they can call the function claim. And by the way, this is another point. Because all these contracts are public, everyone can see them and everyone can call their functions, right? So anyone else on the network can decide that they want to call the function claim. As long as they have a value of X that satisfies this if condition, the contract pays them all of its money. Okay. So I'm going to write this with a different color because it's probably someone else. So if I know a solution X, I create a new transaction that calls the claim function, that calls cpuzzle.claim and gives it X. Now, again, the really important point here is that everyone reaches a consensus about the state of every contract and about the execution of that contract. So if someone finds a valid solution and if they create this transaction, the transaction goes on the blockchain. As soon as the transaction is added to the blockchain, everyone on the network will execute this function. So everyone on the network will see that this if passes, X has the correct hash, and everyone on the network will see that the contract is now paying someone, the person who called this function, right? So everyone on the network reaches a consensus that the money now belongs to whoever called this function. So basically, we just have a much more advanced kind of consensus. We have consensus about how much money each person has. And we also have consensus about the state of every contract and the code of every contract. Now, one thing breaks here, and the thing that breaks is that I can no longer have the UTXO model that I had in Bitcoin. I cannot have this kind of transactions with inputs and outputs. So actually, I was kind of lying to you here. Instead, I'm going to have accounts. It's like for every public key, you're going to just keep track of the balance of that public key. See, this was not what we were doing in Bitcoin. In Bitcoin, we said that there are a bunch of coins. And whenever you create a transaction, you have to say exactly which one of your coins you want to spend. In Ethereum, we're going to say every public key is going to have a balance, and everyone is going to keep track of everyone else's balance. So if my public key has a balance of 10 Ether, I can spend up to 10 Ether. And I don't have to say which particular coin I want to use. And the reason for that is because, well, I have these transactions like this where a smart contract is paying someone, and it's just nonsensical if I have a ton of outputs here, right? Okay, so this part, these inputs and so on, they're not really coins anymore. It's just that the person who's creating this transaction has an account balance, and they're saying, I want to pay this much in transaction fees from my account balance. Okay. Now, if you remember one thing from this course, it's that consensus is important. So we have to make sure that everyone on the network always gets the same results. Now, of course, our blockchain protocol, we've talked about it in depth in this course. It's going to give us a consensus on the history of transactions. So everyone on the network is going to agree what the previous transactions were and what was their order. But everyone on the network should also agree on the result of executing the code. So your programming language cannot have any kind of ambiguity. If different nodes are running the same program, they should always get the same result. Okay? So you cannot have undefined behavior. You cannot have something like divide by 0 in C or C++ where it's left up to the compiler to decide what to do. Everything should be exactly defined, and every program or every function call should have exactly one possible execution, which also means that you cannot have random behavior or non-deterministic behavior, because again, everyone has to reach a consensus. Okay. Now, can you see an attack on this one? We have 2 minutes. Give me an attack on this contract. Yes. Well, okay, that's actually a good idea, but not the attack I had in mind. So if you solve it once, you can call claim several times. But that wouldn't actually help you, because this one, this cpuzzle.balance, is basically the amount of money that cpuzzle has, right? So this is not going to work. The first time it's going to give you all the money, but the second time it has 0 money, so it's just going to give you 0. But in general, this is another reason why we keep track of balances for all the people and also all the contracts, because a contract cannot create new units of money either. Right? So a contract can only spend money that was previously transferred to that contract. So if a contract has, let's say, 10 Ether and tries to spend 100 Ether, our programming language would just throw an exception. It would just cancel the transaction. Right? So yeah, unfortunately, there is no infinite money loophole, but there is another attack.
Ethereum mining implemented in Solidity.
Sorry?
Is the Ethereum mining process implemented in Solidity, or
no? You can do the mining with whatever approach you want. And actually, right now, Ethereum is not using proof of work anymore. We will talk about proof of stake. But the issue here is actually with the miners. So imagine that I solve this problem. Imagine that I find a solution. I find an X that has the correct hash. What do? I create a transaction, and that transaction is calling this cpuzzle.claimX. So it contains a pointer to cpuzzle. It contains the name of the function I want to call. And it also, importantly, contains the solution X. So suppose you're a miner now. You see this transaction. And when you see this transaction, you realize that, well, whoever makes this transaction is going to get a lot of money from this smart contract. So why would I put your transaction into my block? I would just create a different transaction by myself, which basically steals your value of X. And then I would put my own transaction into the block that has the correct value of X. And then the contract pays me. So this is what I call a front-running attack. And we're going to have a lot of fun with this kind of attack in this course. So every time you write a smart contract in this course, you have to figure out if it's vulnerable to front-running. Because remember, we don't trust anyone, including the miners. So the miners might just try to steal the money from you. But this kind of front-running, it's not just done by the miners. Actually, anyone on the network can do this, right? Because when I create this transaction, miners will be more successful. But anyway, when I create this transaction and I give it to my neighbors in the gossip protocol, why would they propagate the transaction when they can just create their own transaction, stealing my X value and propagating their own transaction, right? So again, we don't assume that anyone is honest. In this course, we just assume that everyone is rational. And rational means that they want to maximize the amount of money that they make. And they don't care about anything else, okay? So this is the front-running attack. I'll see you tomorrow, and we will start coding from tomorrow.